Annapolis, Maryland, May 1945. The war in Europe was over, but in the cavernous, dimly lit warehouse of a naval laboratory, a different kind of shockwave was just beginning to reverberate. Dr. Robert Goddard, a man whose name was synonymous with American rocketry, stood motionless before the object that rendered his life's work both validated and utterly obsolete. The ailing physicist, his body frail and his voice reduced to a hoarse, painful whisper by the throat cancer that would claim him within months, slowly reached out a hand. His fingers traced the cold, hard lines of the aluminum skin. This was not one of his own creations, painstakingly built and launched in the New Mexico desert. This was something else entirely. This was the German V-2 rocket. For 20 years, Goddard had been America's lone prophet in the wilderness of rocketry. While the world ignored him, he had pioneered the fundamental principles of liquid-fueled rocketry on a shoestring budget, funded by the reluctant philanthropy of the Guggenheim Foundation and his own unshakable belief. He had patented the multi-stage rocket, the liquid fuel engine, and methods for steering and stabilizing a rocket in flight. His pleas to the U.S. military for support had been met with polite disinterest, filed away as the fantastical musings of a brilliant but eccentric dreamer. He had worked in isolation, a genius with a handful of loyal assistants, battling not only engineering challenges, but also the profound indifference of his own nation. Now, surrounded by Army ordnance officers and Navy engineers in this anonymous warehouse, Goddard was confronting a devastating truth. The Germans hadn't just built a rocket, they had built an entire industrial ecosystem around rocketry. They had taken the theoretical concepts he had pioneered and transformed them into a weapon of war on a scale he could never have imagined. America, he realized with a sinking heart, had been asleep at the launch pad. The V-2 was not merely an advanced prototype. It was a fully operational, mass-produced missile system. As he circled the 46-foot behemoth, he saw familiar concepts everywhere. The use of liquid oxygen and alcohol as propellants, the gyroscopic stabilization, the concept of thrust vectoring. It was like looking into a dark mirror, a vision of what his own program could have become with national commitment. What Goddard couldn't fully comprehend in that single afternoon was the sheer depth of the technological chasm the V-2 represented. This examination would reveal that the Germans weren't just a few years ahead. They had leaped over problems American scientists hadn't even identified yet. The rocket in that warehouse was a brutal piece of evidence. It proved that while America had a lone Robert Goddard, Germany had Peenemünde, a sprawling state-funded research complex employing thousands of scientists and engineers, backed by virtually unlimited resources and a 7-year head start with a singular terrifying focus: to weaponize spaceflight. The V-2's very existence was a monument to a parallel universe of technological progress. Its engine produced 60,000 pounds of thrust, a figure so staggering it seemed like science fiction to the few American engineers who had seen Goddard's rockets, the most powerful of which had managed 985 pounds. The Germans hadn't just achieved this in a lab. They had perfected it on an assembly line, producing over 600 of these technological marvels per month in an underground factory built by slave labor. The precision of its machining, the sophistication of its guidance computer, the sheer audacity of its steam-driven turbopump, all of it spoke of an industrial and scientific maturity that the United States, for all its manufacturing might, simply did not possess in this field. In a letter to his patron, Harry Guggenheim, Goddard would later write, with a bitterness he could barely conceal, "The Germans have used my patents. They have taken concepts I developed and built them at a scale I could never achieve. The V-2 is what my rockets could have become if anyone in America had listened." But in that moment, in the Annapolis warehouse, the personal tragedy was eclipsed by a larger, more frightening realization. The future of warfare and the key to the high ground of space had been forged in Nazi Germany, and the United States was now holding the blueprint years too late. This was not just the end of one war, it was the terrifying beginning of a new technological race, and America was already desperately behind. The silent, imposing form of the V-2 was not just a trophy of war. It was a wake-up call, written in steel and ambition. A challenge that would define the next quarter-century of American science, politics, and destiny. The initial discovery that would ultimately deliver that captured V-2 to a Maryland warehouse and shatter American scientific complacency began not in May, but in the chaotic, mud-churned days of mid-April 1945. As the Third Reich crumbled, American forces of the 3rd Armored Division, known as the Spearhead, raced across central Germany. Their objective was to secure territory and capture key assets before the advancing Soviet Red Army. On April 11th, probing the forested slopes of the Harz Mountains near the town of Nordhausen, a patrol stumbled upon a nondescript railway entrance leading into the Kohnstein Mountain. What they found inside would defy all previous Allied intelligence about German industrial capabilities. Descending into the dank, cold depths, the soldiers switched on their flashlights, the beams illuminating a sight that seemed to belong more to a dystopian novel than to reality. This was the Mittelwerk, or Central Works, a subterranean factory complex of unimaginable scale. Tunnels, reinforced with concrete and stretching for miles, branched off into a labyrinth of production halls. The air was thick with the smell of oil, metal, and decay. Instead of the expected stockpiles of small arms or Panzerfausts, the GIs found rows upon rows of partially assembled V-2 rockets, lined up on conveyor systems like silent, skeletal giants. The cavernous spaces echoed with a ghostly silence, but the evidence of frantic, recent activity was everywhere. Warehouses were packed with thousands of components, fin assemblies, nose cones, delicate-looking instrument panels, and massive combustion chambers. In offices, technical drawings were strewn about, as if engineers had fled just moments before. But the most harrowing discovery was the human cost. The soldiers found emaciated, barely alive prisoners, clad in ragged striped uniforms, the survivors of the nearby Mittelbau-Dora concentration camp. They had been the enslaved workforce that built this technological marvel. An estimated 20,000 to 30,000 prisoners died from starvation, disease, and brutal execution while assembling the V-2s in these hellish conditions, a death toll that exceeded the number of people killed by the rocket itself in combat. The V-2, a symbol of futuristic engineering, was built on a foundation of unparalleled barbarism. The American infantrymen, hardened by the horrors of the European campaign, were nonetheless stunned by the industrial efficiency of this underground hell. Word of the discovery raced up the chain of command. Among the first technical experts on the scene was Major James P. Hamill of the Army Ordnance Corps. Walking through those vast, dimly lit tunnels, his sense of disbelief grew with every step. He wasn't just seeing a weapons factory. He was witnessing an industrial achievement that seemed impossible for a nation supposedly on the brink of collapse. The Germans had not only mastered the rocket science, but the immense logistical challenge of its production. The precision machining of 50,000 individual parts per rocket, the quality control, the coordination of subassemblies deep within a mountain. It was a feat that dwarfed anything in the American arsenal. Hamel, however, understood a strategic implication that the frontline soldiers could not. The Harz Mountains were deep within the zone of Germany slated for Soviet occupation, an arrangement decided at the Yalta Conference. The Red Army's arrival was a matter of weeks, perhaps only days. A terrifying realization dawned. Every V2 component, every blueprint, every technical manual in this facility would fall into Joseph Stalin's hands, handing the Soviet Union the very same revolutionary technology. The emerging Cold War landscape was being drawn in that instant deep under the German mountain. The United States had a fleeting closing window to deny this prize to its soon-to-be rival. Within hours, an urgent cable from Washington landed on the desk of Colonel Holger N. Toftoy, the chief of the Army Ordnance Technical Intelligence in Europe. The orders were clear and unequivocal. Get the rockets, get the documents, get the scientists. Get them out before the Soviets arrive. This directive launched Special Mission V2, one of the most critical and clandestine intelligence operations of the war's final days. It was a desperate race against the clock, a logistical nightmare undertaken in a largely lawless, war-ravaged country. Under Hamel's and Toftoy's direction, American troops and engineers worked around the clock, their efforts illuminated by generator-powered lights in the eternal night of the tunnels. They weren't soldiers anymore. They were warehouse movers on a history-altering scale. They carefully crated up complete V2s and subassemblies, loaded tons of technical documents onto trucks, and directed a seemingly endless stream of flatbed rail cars into the mountain's hidden sidings. The operation was a masterpiece of improvisation and determination. When they were done, an astonishing 341 rail cars had been filled with the spoils of the Mittelwerk, enough hardware to build approximately 100 complete V2 rockets. This colossal train, a rolling treasure trove of Nazi technology, then began a perilous journey northwest, racing across a fractured Germany towards the port of Antwerp. There, waiting Liberty ships, their holds gaping open, would carry this captured future, this Operation Paperclip in hardware form, across the Atlantic to the United States. The seeds of the American space program and the means to understand the terrifying technological gap were now on their way, snatched from the grasp of the Soviets, in a breathless, last-minute heist that would reshape the 20th century. By late May 1945, the first components from the Mittelwerk began arriving at their new home, the White Sands Proving Ground in the vast, sun-scorched Tularosa Basin of New Mexico. It was a landscape of stark contrast to the damp, oppressive tunnels of the Kohnstein Mountain. Here, under the relentless desert sun, Army engineers began the monumental task of unpacking, cataloging, and ultimately understanding their captured prize. With each crate they pried open, with each technical drawing they unfurled on makeshift tables. The sheer magnitude of the German achievement became clearer and more profoundly disturbing. This was not merely reverse engineering a new weapon, it was an archaeological dig into a more advanced technological civilization. The V2 rocket, designated A4 by its creators, was a masterpiece of systems engineering. Its basic specifications were impressive enough. 46 feet tall, weighing 28,000 pounds at launch, capable of hurling a 1-ton warhead over 200 miles. But these numbers were just the preamble. The real revelation, the series of gut punches to American confidence, came as teams of the nation's best engineers began the meticulous process of disassembling the rocket, subsystem by subsystem, and discovered that every component represented a leap of logic and materials science. The heart of the beast was its engine, a massive combustion chamber at the base of the rocket. To American engineers familiar with the sputtering experimental firings of Robert Goddard's designs, the reported performance of the V-2's engine was staggering. It produced 60,000 pounds of thrust. Goddard's lifelong work had culminated in an engine that achieved 985 pounds. The Germans had created something 60 times more powerful, and they hadn't just built one. They had built hundreds, each one a testament to a manufacturing prowess that seemed alien. Dr. Theodor von Karman, the renowned director of the Jet Propulsion Laboratory at Caltech, was summoned to White Sands. His team had been struggling for years to develop the small, tactical, Corporal missile for the Army. After examining the V-2's propulsion system, his assessment was blunt and devastating. We are at least 7 years behind. The propulsion system alone was a cascade of breakthroughs. The combustion chamber used a brilliant double-wall design. The liquid alcohol fuel was circulated through the outer jacket before being injected into the chamber. This simple-sounding idea, called regenerative cooling, performed two critical functions simultaneously. It prevented the paper-thin chamber walls from instantly vaporizing under the 5,100-degree Fahrenheit inferno of combustion, while simultaneously preheating the fuel for greater efficiency. It was an elegant solution to one of rocketry's most fundamental and destructive problems. But it was the turbopump that truly inspired a mixture of awe and despair among the American engineers. This was the component that separated a powerful laboratory experiment from a practical, large-scale rocket. At the heart of every V-2 sat a compact, steam-driven turbine that spun at an incredible 5,000 revolutions per minute. This turbine powered twin centrifugal pumps that were not merely moving fuel. They were forcing 125 pounds per second of liquid alcohol and cryogenic liquid oxygen, 297 degrees, into the combustion chamber against immense pressure. The turbine itself generated over 600 horsepower in a package the size of a small barrel. American engineers stared at this device, understanding that it wasn't just a pump. It was a symphony of advanced metallurgy, precision machining, and mechanical engineering that simply did not exist in the United States. The turbine blades were forged from nickel-chromium alloys that could withstand insane rotational forces and thermal stress. The seals had to contain violently boiling liquid oxygen while spinning at speeds where a microscopic imbalance would result in a catastrophic explosion. Lieutenant Commander Robert Truax, a brilliant Navy rocket engineer, captured the sentiment in his official report. The German turbopump is not simply ahead of American technology. It is technology we do not possess. Then came the guidance system, and with it, another profound revelation of American backwardness. The V-2 did not fly blindly. It was steered by an analog computer known as the Mischgerät, mixing unit, a complex assembly of gears, relays, and potentiometers developed by Helmut Hölzer. This mechanical brain integrated inputs from two free gyroscopes, which maintained the rocket's orientation in pitch and yaw, and a revolutionary new instrument, a pendulous integrating gyroscopic accelerometer, PGA. This device didn't just measure acceleration, it mathematically integrated it over time to calculate the rocket's velocity. When it determined that the missile had reached its target velocity of around 3,500 mph, it sent the command to cut the engine. The sophistication of this system, a fully electronic active control system, was decades ahead of anything in aviation. Dr. Charles Stark Draper of MIT, America's undisputed master of guidance technology, examined the system with professional reverence. He noted the Germans had solved the integration problem, creating the world's first functional fly-by-wire system. The final, humbling layer was the manufacturing quality itself. Every component, from the massive fuselage sections to the smallest electrical connector, exhibited a finish and precision that exceeded American peacetime commercial standards. Welds were perfect and seamless. Tolerances were held to thousandths of an inch. Components subjected to high stress were noticeably overbuilt, with safety margins that American designers, constrained by wartime material shortages, would have considered wasteful. An Army ordnance officer, inspecting the turbopump assembly, scrawled in his notes, "This is engineering from a nation with the resources to build things right, not engineering from a nation scrambling to build things cheap." The V-2 was more than a collection of advanced parts. It was a physical philosophy, a lesson in technological commitment that America was only just beginning to learn, one disassembled piece at a time. The classified reports flowing from White Sands to the War Department in the summer of 1945 carried a unanimous and alarming conclusion. The V-2 was not a singular wonder weapon. It was the herald of a new era of warfare. The United States faced a critical strategic vulnerability. The Germans had proven that ballistic missiles could strike targets hundreds of miles away with no possible defense. And now, intelligence confirmed the Soviets had overrun Peenemünde and the core V-2 production facilities in their occupation zone, capturing not just hardware, but thousands of German technicians and engineers. The race was no longer about understanding the past. It was about surviving the future. America was on the verge of losing the next war before the last one had even officially ended. This stark assessment led directly to one of the most controversial and morally complex decisions of the 20th century: Operation Paperclip. The name derived from the paperclips used to attach the files of selected scientists to ordinary immigration forms, belied its monumental scope and ethical burden. The logic was cold and pragmatic. Hardware and documents were not enough. The true treasure was the intellectual capital, the tacit knowledge, the engineering intuition, the years of trial and error experience locked inside the minds of the men who had conceived the V-2. In September 1945, under a secret directive approved by President Truman, Wernher von Braun and the first contingent of 126 German rocket scientists arrived at Fort Bliss, Texas, under military custody. They were given contracts to work for the U.S. Army. These were not just engineers. They were the architects of Hitler's vengeance weapons. Many were members of the Nazi Party. Some, like von Braun, held honorary SS ranks. Their rockets had terrorized London and Antwerp, and the underground factories where those rockets were built were scenes of unimaginable human suffering, where slave laborers from the Mittelbau Dora camp died in greater numbers than the victims of the weapon itself. The moral compromise was profound and deeply troubling to many within the military and the American public. Were they welcoming war criminals? Were they legitimizing a regime built on genocide by embracing its most brilliant technicians? The debate raged in classified memos and quiet conversations. But the prevailing argument, forged in the icy dawn of the Cold War, was one of necessity. The Soviet Union, under the leadership of their own captured German Helmut Guttrup, was already reassembling the V-2 program at their institute in Bleicherode. To leave this knowledge for the Soviets, while America started from zero, was deemed a far greater risk. It was a Faustian bargain for the soul of American technological supremacy. Meanwhile, at White Sands, the practical challenges began. The first static test firing of a captured V-2 engine on March 15, 1946, was a nerve-wracking event. The first launch attempt followed on April 16th. At 2:47 p.m., a reassembled German rocket, painted in American markings, lifted off from the New Mexico desert. The result was a humbling demonstration that possession did not equal mastery. The rocket's guidance system failed almost immediately, a fin tore away, and it veered wildly off course, crashing into the desert after reaching a pathetic altitude of only 3.4 miles. It was a stark lesson. Colonel Harold R. Turner, the commander of White Sands, watched the fireball and remarked grimly to his staff, "We have the hardware. We have the men who designed it. But we don't have the industrial infrastructure that built it, the experience base that developed it, or the institutional knowledge that comes from 6,000 launches." The Germans had conducted that many test firings and combat launches. The Americans were truly starting from zero. Over the following years, 67 captured V-2s were launched from White Sands, with mixed success. Only about 68% of the flights were considered partially or fully successful, a failure rate that would have been catastrophic in combat. Yet each launch, whether a triumph or a fireball, was a priceless data point. They were America's crash course in high-altitude rocketry. Scientists from universities and burgeoning aerospace corporations scrambled to hitch rides on these projectiles, sending up instruments to measure cosmic radiation, cameras to photograph the Earth, and sensors to sample the upper atmosphere. On October 24, 1946, a V-2 carried a 35mm motion picture camera to an altitude of 65 miles. It captured the first grainy black and white photographs of Earth from space, our planet's curvature starkly visible against the black void. The image was a historic first, a preview of a new perspective on humanity. But it was also a poignant reminder. The ability to send a payload beyond the atmosphere and return data, a foundational capability of the space age, had been delivered to America by a weapon of terror. The path forward was being illuminated by the fiery, often erratic, trail of the past. The German scientists were no longer just prisoners or employees. They were becoming teachers in the most urgent and expensive school the United States had ever attended. The captured V-2 rockets and the German mines that accompanied them were never intended to be the final goal. They were a bridge, a desperately needed prosthetic to replace a missing limb of American technological capability. The true objective, born from the shock of that initial discovery and hardened through the repeated, often explosive lessons at White Sands, was to build a Native American rocketry program. By 1948, the Army Ordnance Department consolidated this effort, selecting Redstone Arsenal in Huntsville, Alabama, as its permanent rocket research center. In a move rich with symbolism, Werner von Braun and his growing team of German engineers were transferred there, now joined by a fresh generation of American engineers, physicists, and metallurgists. The task was no longer to reassemble German rockets, but to absorb their principles, adapt them to American manufacturing, and ultimately transcend them. The first major fruit of this collaboration was the PGM-11 Redstone, a direct and acknowledged descendant of the V2. Its first test flight in 1953 was a milestone. While it used the familiar combination of liquid oxygen and alcohol and relied on a turbo pump and gyroscopic guidance, it was not a mere copy. It was an evolution. American improvements were woven into its design: better fuel efficiency, a more reliable and simplified guidance system, and adaptations for the nuclear warheads it was designed to carry. Most importantly, it was built using American manufacturing processes and materials, a critical step in weaning the program off captured German tooling and know-how. The Redstone became the workhorse of the early American space program, the trusted booster that would later launch the first American astronauts on their suborbital hops. By the mid-1950s, the frantic effort to close the gap was finally yielding results. The technological chasm that had seemed so vast a decade earlier was narrowing. American industry, with its unparalleled capacity for mass production and quality control, had caught up and was beginning to innovate. The Jupiter, Thor, and Atlas missiles that emerged were no longer derivatives. They represented genuine indigenous American rocket technology. They were built by American companies like Douglas and Convair, using American alloys, American electronics, and an American design philosophy that increasingly valued lightweight efficiency over German over-engineering. The Atlas, with its revolutionary, ultra-thin, balloon-like, pressure-stabilized steel skin, was a masterpiece of American ingenuity, a machine that the V2's designers would have found alien and brilliant. Then came the moment that validated every difficult decision, every dollar spent, and every moral quandary faced since 1945. On October 4, 1957, the Soviet Union, using rockets derived directly from the V2 and built with the help of their own captured German engineers, launched Sputnik. The shockwave was global, but in the United States it was a profound national trauma. The technological superiority America had assumed was its birthright had been publicly usurped. The beep-beep of the satellite was a stark reminder of the warehouse in Annapolis and the tunnels of Mittelwerk. America had been warned, but now it had been surpassed. The response, however, demonstrated how far the nation had come. There was no need to start from scratch. Drawing on the foundation laid by the V2 and the Redstone, von Braun's team at the newly formed NASA's Marshall Space Flight Center quickly readied a Jupiter C rocket, a direct descendant of their work. On January 31, 1958, it launched Explorer 1, America's first satellite, into orbit. The gap, once measured in decades, was now measured in months. But the ultimate testament to this decades-long journey from technological inferiority to supremacy was the Saturn V. The rocket that would carry Americans to the moon was the antithesis and the apotheosis of the V2. Designed by von Braun's team at NASA, its 5 F1 engines in the first stage were a declaration of American industrial might. Each engine produced a staggering 1.5 million pounds of thrust, 25 times more powerful than a single V2. Standing over 360 feet tall, it dwarfed the 46-foot German missile. Yet, its technological lineage was unmistakable. The principles proven in the V2 were all there, scaled to an almost unimaginable degree. Regenerative cooling in the massive engine nozzles, turbo pumps of heroic proportions, forcing propellant into the combustion chambers, gimbal-mounted engines for thrust vectoring, and a guidance system infinitely more complex, but conceptually descended from the Mishgaret. The V-2 was the acorn. The Saturn V was the oak. When Wernher von Braun stood at Cape Canaveral in July 1969, watching the Apollo 11 mission launch atop the Saturn V, he was witnessing the culmination of the path that began in the mud and secrecy of Peenemünde. He later reflected, "We always knew it was possible. The physics were clear even in the 1930s. What changed was not the science, but the commitment. America in 1969 could do what Germany in 1945 could not: focus the resources and will of an entire nation on reaching beyond Earth, not as a weapon, but as an achievement of the human spirit." Looking back from the 21st century, the legacy of the V-2 in America is complex and indelible. It was a weapon of terror that achieved little military value at an enormous, horrific cost in enslaved lives. Yet it was also the world's first practical ballistic missile, the first human-made object to touch the edge of space, and the undeniable technological foundation for the space age. For the American scientists and engineers who examined those first captured rockets, the experience was a humbling lesson that would shape national policy for decades. It taught that technological superiority is not a permanent state, but a perishable commodity, requiring sustained investment, institutional support, and the understanding that individual brilliance cannot substitute for an organized national effort. The warehouse in Annapolis is long gone, but the revelation it housed changed history. From that moment of painful recognition, the understanding of how far behind America had fallen, sprang the determination to catch up, the monumental investment in rocketry, and the immortal achievement of human footprints on the moon just 24 years later. The V-2 was conceived as a weapon of vengeance. For America, it became something else entirely: a teacher, a catalyst, and a challenge to look beyond the horizon, a challenge that a nation, once awakened, proved supremely capable of meeting.